because I have to go to work the next day and stuff. My usually just lets me go to bed at 9 o'clock or whatever. She takes care of getting the kids to bed and stuff. So. All right, so you just walked into my class. Get out your notebooks, your piece of paper. This is my demo lesson for you guys, okay? So let's say, so this is the start of my lesson. Let's say that you know, so here's our problem for the day. You know the area of a rectangle is 3x squared minus 8x, and that the length is x. What is the width? So what I want you to do is, I want you to think about that problem. I want you to draw a picture out first. So take about 30 seconds, draw a picture out first yourself. And then go ahead and discuss with your partner, somebody near you, how you might find that answer. Go ahead.
So much about triangles,
I learned it for 3 weeks. Supposed to discuss it. We're supposed to
Now, after you get your picture drawn, I want you to go ahead and discuss. You don't have to solve it on your own. Solve it together. Discuss how you might solve the problem.
Why are you doing that?
For my year long, 3 weeks straight.
That was actually 4 weeks.
4 weeks.
That was over 4 weeks, wasn't it?
So
They did
3x
the diagram
squared
theory
minus
for about 5
8x
weeks.
equals x times
I
some.
think they went not after
You
1
can
week.
background.
Let's see if it'll drawn out.
So x
Alright.
times w
4.
is the
We're all
width,
gonna
Yeah.
or is the area.
So you got
And then we
X
can
times
divide,
the width is that.
divide by x.
So 3x minus 8. Yeah, because 3x squared minus 8x is equal to x times w.
Yeah.
So to get w by itself, divide by x.
Who wants to draw their picture up on the board and then explain to us how you got your solution? Anyone? Or I randomly choose something?
Sure.
All right, Maddie, go ahead.
my hip just popped.
That's getting right.
Yeah.
What?
That's correct.
Okay.
We need to get back in the gym.
My picture is probably not.
I'm just
Not getting straight to me today.
So we said that the area is equal to the length times the width, and the area is 3x squared minus 8x, and the length is x minus the width. So then to find the width, you have to do opposite multiply, which is divide both sides. So the width is 3x minus 8.
Okay. All right, so based on what you have here then, and we could say, we have two different representations for the area. I gave you the area as 3x squared minus 8x, and you also, based on area being length times width, you now have the area as the product of two expressions, length and width. What's the length?
X.
X. And what's the width?
3x minus 8.
3x minus 8. So we are claiming then that these two things are equal, is that right? We're claiming these two things. They're just in different forms, right? This is just, that is this, based on what we've done in the past, multiplied out, right? If I distribute this out, so I could check that by distributing this out, right? If I take x times 3x, do I get 3x squared? If I take x times negative 8, do I get negative 8x? Is there any way that you could think about that we could use our graphing calculators and what we know about graphing to visually show that these two expressions are equal? What might we do to visually show? Colin?
You could just substitute any number in for x.
Okay, we could substitute, so you're saying just substitute any number in, so you're saying go to, just take 3x squared and say 3 times what number you want to plug in?
1.
3 times 1, and then square, and then minus 8 times 1, right? And we get negative 5, and if we put 1 times 3 times 1 minus 8, and we get negative 5. Okay, that works. Now, does that show that it works for every number, though? Just shows it works for 1. Think about what we've done in the past with graphing expressions and how we might show that these two expressions are actually the same. I've never done this before, but if I graph 3x squared minus 8x, I'll certainly get something, whether we know what it is called or anything, we'll get some graphical representation of it. But if I claim that the other expression, x times 3x minus 8, is the same, when I graph this, what should I get? I should get the same thing, right? I shouldn't see any other picture. Now what I don't know is, I don't know if it's off the screen or not. So what I might be able to do is come over here and change this here to, what I like to use is this little bouncing ball. And so when I hit graph, the first one will graph that, and the second one will graph, I'll show you where it's graphing, but it was graphing the same thing. Any other thoughts on how I could verify that these were actually the same? What else can I look at?
After doing that, can you check the tables?
Yeah, I can just check the table. I can check the table here. And again, you're only checking as many points as the table has. But between the two, you can convince yourself. I wouldn't say it's a proof or anything, but you can convince yourself that this is the same. So, okay. Somebody, Gary, will you please read our first objective for the day? What do I want us to walk away learning today?
Use the greatest common factor and the distributed properties factor column.
Okay, so we are going to use the greatest common factor. That should be a phrase or a word that is familiar to us. What is the greatest common factor? Can you tell me what the greatest common factor of, let's just say, two numbers is? So if I put up something like 8 and 12, and I said, what is the greatest common factor? You can tell me, I heard somebody say it, what? 4, but in words then explain what the greatest common factor is. You probably have this in your notes someplace, or you can look it up in your textbook while you're have your notes out now. But what's the definition of greatest common factor? What is 4? You know the answer is 4, but what is 4? It is the what?
It's the largest number that can be divisible by both numbers. Or that can okay.
I know it's hard to explain it, right? It's the largest number that what?
That can be divided into.
Divided into, right? Okay, the largest number that can be divided into each of these numbers. Okay, 4 goes into 8 3 times, and 4 goes into 12 2 times, and 4 goes into 12 3 times. Okay. All right, so we understand what the greatest common factor. So what we're going to do is we're going to use the greatest common factor and the distributive property to factor polynomials. So we know what polynomials are, but we don't really know what factoring means. Second objective is what, Brittany?
Solve problems that involve the need to factor polynomials.
And you actually already did this. The first problem there, you actually did it. You might not have known you were doing it, but you actually did use factoring polynomials to solve or solve problems. John, read the third one.
Explain what it means to factor in polynomial.
Okay, we won't get quite into that yet, but explain what it means to factor a polynomial. Just like the greatest common factor, at the end I want you to be able to define what a polynomial actually is, okay? And the other ones, I want you to appreciate the need for algebraic reasoning and manipulation in order to solve problems. So hopefully you'll see the usefulness of this. And also, when you work cooperatively, I want you to be able to do that with your peers, as you've already done a little bit there. So, okay. What if I asked you to let's take the number 24. What I want you to do is I want you to factor it. There at your desk there, I want you to factor 24. How would you, if I just said factor 24? So this has nothing to do with polynomials, but I just say factor 24. Writing down all of the factors of it, right? Okay.
The factor tree. That's
But
what
you took it all the way down to prime factor,
Yeah.
right? Okay. Well, okay, we got to decide what we might not even be fully aware of what factoring means. So hold on, let's see. Let's go back and just define factoring. So I would say this. I might say this. To factor a number means to write it in terms of the product of numbers. Now, I fully expected you for not everybody to have the same thing in this problem, because when I say to factor a number, it just means to write it in terms of the product of numbers. So there are many ways you can factor 24. I mean, write it in terms of products. Give me one. Brittany, you wrote a lot of them down. Give me one.
6 and 4.
6 times 4. But Gary, you wrote down other ones. 24 is what?
8 times 3.
Now, you can say that the factors of 24 are 4, 6, 8, and 3, but you can't say that 4 times 6 times 8 times 3 is 24 factored. You understand the difference there? So if I just say to factor it, now though, there's something else that, like at least John was doing, which is not wrong. He broke all of these factors, and these aren't the only ones, right? I mean, you can say, what, 12 times 2, 24 times 1, right? But he took it one step further, and he broke these numbers down into what? Prime. That's a little different. To prime factor means to break a number down into the product of its prime factors. So in this case, 24 is what then? And John, you probably had it. What is it, Cat Cole? What's our, what?
Do you want it 2 cubed times?
Oh, it doesn't matter. 2 cubed and 2 times 2 times 2 is the same.
Alright, 2 times 2, yeah, times 3.
2 times 2 times 2 times 3, right? Okay? Now, how many ways are there to factor 24? 4 ways, only if you're looking at what kinds of numbers? Because what about 48 times a half? Are those factors? Sure. So usually though we only talk about factoring over what kinds of numbers? Integers, right? So even integers then you might say 4, but then what about negatives, right? Because negative 6 times negative 4, so usually we even mean just the positive integers. So technically there's probably an infinite number of factors until we specify what kinds of, or over what set of numbers we're factoring. However though, when it comes to prime factors, that's the key. When it comes to prime factors, how many ways are there to factor any number? How many ways are there to factor any number? Just one, with prime factors, okay? All right, so that's with 24. What about if I said to factor 56x cubed y? Factor 56x cubed y. Now I just said factor it. So again, just write it as a product of 2 factors. Write as a product of 2 things multiplied together. I'll try not to get too close to Colin, what do you got? 56x cubed y is what?
X cubed y times 56.
Times 56. There you go. Somebody give me another. Gary.
8 times 7
8 times 7.
times x squared.
Oh, so you're going with a little more times x cubed?
Yeah.
Oh, sorry, x cubed. Times y? Okay. Now, obviously, if you were wanted to prime factor, you get 2 times 2 times 2, right? All right, let's try another problem here. Similar to the first one, and some of you might have had a little problem with the first one, but that's all right. What if, I think you'll get this one, what if the area was 10y squared plus 5y, and you know that the length is 5y. What would the width be? What would the width be? Go ahead and solve that. If we knew the area was 10y squared plus 5y, and we knew the length is 5y, what would the width be? When you think you've got it, go ahead and share it with your neighbors, see if they agree. It's okay, speak loudly. Should be communicating in class.
Just like the first one, it's like
What do you say, Brittany? You and John get the same answer? What is it?
2y plus 1.
2y plus 1. So what you're saying is that, so the answer is 2y plus 1. So you're saying that 10y squared plus 5y equals 5y times 2y plus 1, right? Now if you redistribute that out like we've done a couple lessons before, then you could see 5y times 2y is 10y squared, 5y times 1 is 5y. Now, if you didn't know that it was 5y, is there any other way that you could write 10y squared plus 5y as the factor of two other terms? Discuss that with your group and see how you could write that in another way. But if you didn't know 5y, just 10y squared plus 5y equals, write it in two different ways, or one different way. Okay. What times what? That's not nice.
Well, both of them have 5 y's. You can think of 5 plus 1. Is that what you're talking about?
What's that?
He wants different.
I want different factors. Let's say you didn't know that the length was 5y. So
So you can just say,
can you just say, what are the possible lengths and widths of the rectangle, if you know that? Is there another possibility? Kind of like 24. Does it have to be 8 times 3? Could it be something else? Oh, we decided it could be 6 times 4. What else?
It's really good, Brittany.
What do you guys say? What did Brittany say there, John?
Well, she
Tell us
said
why.
you could do just the factor out of 5.
Okay. And then?
And then you have 2y squared plus y.
Yeah, that would work, right? Now, the difference between these two factors and these two factors, they're the same product, right? The difference between these two is that this one here still has something else that is common to these two terms, right? Whereas these have nothing else in common. So what we would say is we have pulled out, or this right here represents the greatest common factor, okay? So, now we're ready for, now that we've got a little bit of experience with what we're doing, now let's go ahead and define the thing that we are doing today. So here's the definition. Now we know what we're doing here. To factor a polynomial. So here's the thing we want to make sure we can do today. Means to write it in terms of the product of other polynomials. We do this only with integers and it is not complete until we cannot factor anything else out. So we call these prime polynomials that we're left with. Remember what prime means. A number that is prime means that it can't be what any further? It can't be factored any further, right? 7 is prime because its only factors are 7 and 1. All right, because, and I added this integers thing here because, you might say, oh, you can only factor out a 5 here, but think about this. Could you factor out a 10? Well, you're left with y squared plus, how are you going to get 5 from 10? What? Half? So I need half of a y, right? And you can do that all day long. But we only do integers. So we're only factoring over integers, okay? All right, so with that in mind, let's see if you can do your first example. Let's factor, we'll do this one together and then I'll have you do one. Factor 21ab squared minus 33a squared bc. Let's look at this one together. So this time I'm given, this is a polynomial, so it's like I'm given an area. So if you have your visual, I'm given an area and I want to make a rectangle out of it. So I'm given, you don't always think about this, but I'm given an area and I gotta find the length and width. So I just gotta find these two things. Well, there might be many things. I guess I could write it like this. I could write it as A, right? Because they both have an A in it. And I could say A times 21b squared minus 33a, right, bc. But then I factor out everything in that case. No, because I got an A out. Oh, can I factor out any more A's? We've already done Gray's common factor, but can I factor out any more A's? Like Brittany's saying, yeah, no, okay. You were saying, yeah, don't worry. Can I factor out any more A's? No. Can I factor out some B's? Okay, what can I factor out for the B's? 1B. Can I factor out any C's? No. Do they have any C's in common? Going back to what Gary was telling us at the beginning, common. So I know I can get an A and a B out. As far as the numbers go, 21 and 33, that goes back to like the 4 and the 8, right? Or 8 and 12, whatever I did before. What can I factor out of 21 and 33? Calling the sense? 3? So let's pretend then that 3AB is one of my dimensions. Well then, what's that leave me with then? Well, what do I multiply 3AB? I'm just doing the distributive property backwards. So factoring is just the distributive property backwards. So now I'm going to put down your notes up there. Factor is just distributive property backwards. So 3AB times what?
7b.
7b. Well, that gives me 21ab squared. 3ab times 7b. 21ab squared, yeah? Minus what? 11ac. And you should double check. Now, if it's one that you can check on your calculator, you can use that, as well. I think better off is being careful here. Okay. Now you try one. What I want you to try is you factor 6x cubed y, x cubed y squared, plus 14x squared y, plus 2x squared. You factor that. I'll come around and see how you're doing. Nobody made the fatal mistake. Everybody factored out 2x squared, and you got 3xy squared plus 7y, and then 2x squared is 2x squared, right? So you can just leave it. Now be careful with that. It's got to multiply back out, so plus 1. Okay, good. Now I've got a nice visual for us to look at with this. We're everybody taking these algebra tiles that we've used before. And on our class website, I've put the maybe So somewhere it was up, but now I'm getting it up again. I have put this website up here on our class website where if you go home and you want a good visual for what we've been doing today is algebra tiles here. So what I want you to do is, I want you to take out, and I'm going to assume that you have one of these before, but all I want you to take out on your desk is a representation for 3x plus 6. So 3x plus 6 is just 3 of the, we'll call them longs, and then 6 of the little units. Don't worry about the colors. Right now, we'll worry about that later. Now what I want you to do is this. I want you to take those 3x plus 6, and that is just a bunch of, just 3, not this. This, if you remember, this is a square. This is x squared. Just 3x plus 6. And what I want you to do is, right now you just have a random mess that is an area of 3x plus 6. What I want you to do is, I want you to try to make a rectangle. Try to make a rectangle out of it. Didn't quite work, did it? It was close. Yeah, the problem is,
I got different squares.
oh yeah, well maybe that was, yeah, that's weird. So that is not, and you'll see that it's barely off, and that they designed them that way. They are the same, and we've discussed this before. They are the same width here, but an equal number doesn't go into, or an even number doesn't go into it this way. It'll always be off a little bit. So. When you built your rectangle, though, doing that, seems like everybody's doing this then, right? So now let me ask you this. Your 3x plus 6, you have built a rectangle that are what dimensions? What is this dimension down here? How long is that? And then that, what is this? This is an x. Now don't, this is x, and this is 2. So it's x plus 2 on the length. Don't look at like the width part of it, you're just looking at the dimension, the length of that dimension. Across here, this is what? Same as that. 3. So what you've done is you have just rewritten 3x plus 6 as 3 times x plus 2. Is that consistent with the algebraic way of looking and saying, oh, 3x plus 6, the greatest common factor of 3x plus 6 is 3, and so we can rewrite that, we can take out a 3 and rewrite that as 3 times x plus 6. Do another one. Pull out x squared plus 4x. X squared plus 4x. So pull out x squared plus 4x and try to make a rectangle out of that. Now, if you can't make a rectangle out of it, it's already prime. It can't be factored. Hopefully that was pretty easy. But again, I chose this because that is x squared, but the dimension here is just a what? That's just x. So it's not x squared there. The thing is x squared, the object, but this is x. And then this length here is what? What is that? Oh, careful. 1, 2, 3, 4. But this length here is what?
X plus 1.
That length is x. X plus 4. So what you're saying is x squared plus 4 the rectangle formed is x down the width here, or length, whatever we'll call that, and the length of x plus 4. Is that consistent with x squared plus 4x? Greatest common factor between these is x times x plus 4. Consistent there. Try this one just for fun, even though we won't be going here for a few days here. But pull out x squared plus 3x plus 2. Pull out x squared plus 3x plus 2. See if you can form a rectangle out of that.
Mine?
What?
He's cheating.
Why is he cheating? How's he cheating?
Look at mine.
You're looking what?
He's looking
I was looking at yours. Oh, I thought you said looking online. I was like, now if you can build this, which looks like everybody is, if you can build this, you can already factor by the next method, which all we're doing right now is factoring out the greatest common factor. You've got, when you did that, you've got what down one dimension here. What do you have? What's that dimension for you? How long is that? And then plus 2. So this is an x plus 2. So x plus 2 down one dimension. The other one is x plus 1. So what you've already said was that this is x plus 2 times x plus 1. All right, one last problem for you to work on with your partner. Then we'll close up shop for the day. So, the length of Jeremy's garden is, now realistically I probably have these on a worksheet or something, but is 5 feet more than twice its width.
Are we done with these?
Yes, you can put those up. Sorry, I should have collected those. That was bad classroom management on my part. I figured you guys could handle them. This year, Jeremy decided to make the garden 4 feet longer and double the width. How much additional area did Jeremy add to his garden? Now again, normally I would have this already on a worksheet or something like that, so I'll stop right now and I want to have somebody read this and discuss the problem with us. So Gary, go ahead and read the problem to us.
The length of Jeremy's garden is 5 feet more than twice its width. This year, Jeremy decided to make the garden 4 feet longer and double the width. How much additional area did Jeremy add to his garden?
Now let's talk about this problem before we get started on it. So it's got a garden, rectangle obviously, 5 feet more than twice its width. Everybody think you can draw a picture of a rectangular garden 5 feet more than twice its width. That's his garden. That's his garden. Then it says this year he's making his garden 4 feet longer and he's doubling the width. So you're going to do something with the dimensions of the garden, right? It's going to be the new size of the garden. And the question is, what's the question asking us for, Brittany?
How much additional area did he add to the garden?
So he's adding some on his dimensions, so obviously he's adding some area there. The question is, how much did he add? So go ahead and try to solve that. I'll be around to collect your algebra tiles and help you out if you need. And work on that together too. There's all your math there, so I'm just going to run it over. wait, after you find the one, okay? So what's the original? So you're saying the width is 5.1 twice the width of 5.1, so 2w by that. So you have your area, 2w25, okay? And then now you got 4 feet longer on the width and double or on the width and double the area, okay? So you're gonna say, so now this is that, right? So what's that? So how do you find the difference in area? So in the interest of time, and because actually my notes, I did something incorrect on it, that you'll see when I share my lesson plan, but I'm blaming that on sickness. So originally, what do we have? W and 2W plus 5. I forgot the plus 5. So the area there is 2W squared plus 5W, right? The new area, though, is what? Double the width. And the length is, what was it? 4 feet more. So that's 9, right? So this is 2W plus 9 there. So the area here would be 4W squared plus 18W. Now, how much bigger is this than that? How do I find that? Subtract them, right? So difference is the bigger, and we've already done this, minus the smaller, 2W squared plus 5W. 4W squared minus 2W is 2W squared. 18W plus 5 minus 5W would be plus 13W. Okay. Now, here's a question. And this is the answer though. Could we rewrite that in factored form? What can you factor out? A W. So you could write that as W. And this is, either one's right. I mean, this is probably more simplified form, but factored form is useful in some points. So what is that? 2W plus 13? So either one. And technically this is units cubed. I know when you do that, or units squared. When you do that, it gets variables in the way, but that's the Okay, in closing though, just to finish up our time here, what does it mean to factor a polynomial? Share with your partner, share with somebody near you, get a good definition. What's it mean to factor a polynomial? Put your notes if you want. But let's try to now explain it in our own words. Factor a polynomial simply means what? We don't like to give formal definitions all the time. Just to factor a polynomial just means to do what with it? What? Okay, write it as its prime. Write it as a product of prime polynomials, right? To factor it. So factor the things, the factors in a product are the numbers or the things that you multiply to get whatever. And I have one last problem for you to factor, and then you can leave. And I'll just do that for you, because we're not going to leave. So, all right. Anyway, so I did that so you could see several things. Okay. I wrote, and you'll see this on the lesson plan that I shared here for this day. So I wrote a lesson plan for this that you'll be able to see. kind of as a model here. But hopefully you see a couple things, you know, there. I didn't. Well, I guess maybe I should ask you first. I mean, what was there anything about that lesson, that demo lesson, that was not, you know, typical that you have seen? And I know you're not real students and you're not having the discipline issues and administrative, you know, issues and things like that. But I mean, just as far as like the lesson itself being taught, you know, what were some differences or similarities there that you noticed or saw? Or was it pretty typical?
Well, compared to what we saw in the school.
Yeah, yeah,
I mean, you walked around a lot more.
okay. So I tried to walk around a little bit more there too, but, I mean, go ahead.
You had us talking more.
Okay, so I tried to get you guys to share a little bit, you know, there.
There were more like connections between other things.
Okay, I mean, I tried to make sure I made connections with areas. What were you gonna say?
You let us like investigate a lot.
Yeah, I mean, that was one of the things that I hope was made clear. You know, I started out the lesson with like a problem, right? You know, a problem that investigated something, and some people would argue, well, how do you expect them to solve the problem if you haven't taught them the, you know, concept or procedure? Well, because solving a problem doesn't in general have anything to do with concepts and procedures, right? I mean, the concepts and procedures are oftentimes the well-formulated or standard way to do it. It doesn't mean problems can't be solved. You know, people can solve equations by guessing and saying, oh, I think 4 works, and 4 work. Oh, so I can always guess. Well, no, we have our methods for solving because we can't always guess. Okay. So I like to think of it as having students play around with a little bit of the concept before. If you notice, I didn't give, it took me 15 minutes to give the definition of the thing that we're going to do today, right? You know, we were going to factor using GCF, but I didn't share what factoring even meant until later on in the lesson, okay? After we kind of made some connections and solved some problems. So, you know, and even though it wasn't a whole lot for this lesson, you know, I tried to make sure that, because to me, technology is always something that is just there. You know, I tried to integrate it just seamlessly there, not made it as an add-on or, you know, or an afterthought, or tomorrow's lesson we're gonna do this. You know, I didn't use it as a crutch. I just said, hey, here's a visual, you know, for it. And even the online algebra tiles and things like that. So, if you'll notice then, in my example for my lesson plan, you know, I filled in all the stuff. I already shared you those things there, so you can kind of look at it, you know, later on. You don't have to worry about the standards. I just did that myself. Materials, you don't have to put like pencils and paper and stuff like that. But the progression, you should always look and see, you know, what students should already know, what students know or will be doing afterwards. And you notice I actually, you know, I challenged myself and said, well, I'm just gonna do it based on that, you know, what might seem to be a boring lesson from that greatest common factor that we were looking at the other day with objectives. And I thought, well, you know, I mean, hopefully I can pull in something that will allow them to get a visual, do something hands-on with the algebra tiles. And if you notice, you know, I did nothing but pulled out the exact stuff. I wanted to do that. I wanted to make sure I did that. I just pulled out problems from here. I didn't look online. I didn't do anything else, but just pulled out problems from here. Now, the only thing that they didn't do in here was do anything with algebra tiles. No, that's not true, is it? What section was that? Remember where we were?
It was like page 261, I think.
Oh, you know what? Yeah, right here in the side it says lab activity. You can learn how to use algebra tiles to factor by using the distributed property in lab 9 on page A15. So I went to the appendix 15 and it just had some, you know, algebra tile activities on it. But it was all right there, first problem, and it wasn't rocket science. Okay, you have to. I would much rather you focus on explaining well and knowing your content than coming up with fancy, you know, lessons and stuff like that. I think we've lost that art of clearly explaining things. Well, let's look at the assessment then. After my objectives, I wrote and I said, okay, well, how am I assessing it? Or how am I assessing it? And let's see if I did this, okay? At the beginning of the class, I assessed my students' understanding of factoring in general by asking them what it means to factor a number like 24. We did that. That'll help me determine whether they understand the concept or not in arranging one factoring. And you really weren't, okay? Because factoring, we get confused when we say factor. Do we really mean prime factor? Do we really mean just write all the factors? Or do we mean write any factors? And those are different, and people call them the same thing sometimes when we're not explicit. But there is a difference between prime factoring. If I just said factor 24, to me, there's not some it's not universally understood that means to prime factor. Factor 24, 6 times 4, I factored it. Then during class, I'll monitor students' progress. I always want to remind myself, I've got to go up and down the rows and check people out. When you're working, it's not my time to answer emails. I'll ask general questions, both procedural and conceptual. I didn't have to ask a whole lot of questions for you guys because you did well. My main backpop question will be, what does it mean to factor a polynomial? That's what we were asking. What does it mean to factor a polynomial? I probably didn't ask that question enough through, but I also only did a couple examples, which in real class I'd probably have a couple more because you have a little bit more difficulties with it. The response I wanted was to write a polynomial as a product of its prime polynomials. And then as part of my closure, I was going to have you complete a ticket out the door. And then I wanted to also ask, what does it mean to factor a polynomial? Discuss that in your groups. I've got some homework problems there. Where to start? Did I follow my introduction, procedure, and closing? Well, at the beginning of the class, I wanted you to work on the opening problem written in my notes, and I attached my notes, even though there was something incorrect about it. So I just attached my notes. I had these written down. Last problem's incorrect. Then after discussing that problem, I'll share the learning objectives for the day, so that's what I wanted to do. And then my procedures was, led you a discussion of factor 24, how to factor 24, 56x cubed y, and then I gave you another problem concerning finding the width, and from there, after you've had experience with working these few problems, then I wanted to define factoring polynomials. So it's kind of in the middle of my lesson that I say, this is what we're doing. And then a couple examples, again in a real class, probably a couple more. And then distribute algebra tiles. And then to end the instruction, I have one last problem. If I didn't have time, I wouldn't have to do that problem there. That was kind of a fill-in. If I needed to get to my closure, I get to my closure. If I had the time for that last problem there, then I went ahead and did it there. Closure, describe what I was going to do for closure. As far as reflections go, universal design for learning, this is where we say, what are we doing to meet needs of lots of different students, okay? Well, and it's my own analysis, right? And somebody can challenge me on it, and that's fine. I think I can always probably do better. I said this wasn't a perfect lesson, there's something else I can incorporate. Yeah, but incorporating one thing might mean taking something out. But what I do, I try to make as many connections as possible. So I know that helps people. There was problem solving to help motivate students instead of just saying, okay, we're going to factor these polynomials. Here's what's polynomials, and this is what it means to factor, and try to factor these out. I try to incorporate some problem solving. And I know that the problems didn't necessarily involve pulling out greatest common factor. That wasn't the point. I mean, if you think about it, greatest common factor is not difficult. I mean, you can do that in 10 minutes and then give students 5 problems. So it's not a whole lesson. But your textbook does different things. That's why. It shows relationships between all the stuff that you're doing. Just because you're only teaching new content of greatest common factor doesn't mean that you don't do anything else that entire day. I mean, you still have to problem solve. I gave algebra tiles as a visual representation. I thought you had to read carefully in order to solve the word problem. That's why I asked you to read that. Some people like to read and try to understand. The online algebra tiles, and also, let's see. That was weird, it didn't catch. I went back into my other file, I don't know why it didn't. When I attached it, and then I put the, what I did with the graphing calculator, and I thought it would automatically reattach the new one. As far as adaptations, no IEPs, no specific IEPs. And then I always like to reflect on, am I making my students talk to each other, talk to me? I thought I gave you guys an opportunity to talk to each other and sharing with me and the rest of the class. Reflections on formative assessment, a lot of repeat from the assessment part there, but just to think about, what am I doing to formatively assess? So as I'm going, asking questions, I'm watching you guys do things, and so when I think about that, and then possible problem areas for students, where did I think people would have problems? Factoring out the greatest common factor. Of course, that wasn't an issue with you guys, but that will be an issue for my real students. What am I going to do about it? I need to remind them that they have their completed answer. Nothing else can be taken out, so you can check that out. When they're doing the algebra tiles, I pointed that out, that when you have an x squared, doesn't mean your dimension is x squared. Your dimension is x. And that kind of confuses people with algebra tiles usually. Well, so that hopefully gives you an idea, of what I think that, a halfway decent lesson consists of when it comes to teaching. So let's go and look though in our, any other comments about that though? Like I said, it wasn't, I didn't necessarily, there are other lessons that I would do that would lend itself better to even more of a discovery type of thing. That lesson there was, to me, one of the reasons why I wanted to choose it was because to me it was a pretty straightforward and really boring lesson, just greatest common factor, so what? But that doesn't mean that you have to be, it has to be boring, it's not anything, you can still teach it and do some problem solving and get some conversation going and not just teach it as, it is what it is. All right, right now, let's go to your course manuals here because I want to look at pages 69 to 75 because you guys are starting to write lesson plans. It's going to be better all day, but I'm already losing it. And we're not going through all of this because there's a lot of stuff here, but it is for your reference. When you're writing your objectives, you want to try to write them in, and actually, I did not, the class doesn't need to see this, so if you notice what I had you guys read here, I don't know you wouldn't have caught this, but what I had you guys read here doesn't have anything beyond there, but on my actual lesson plan, I do have, after the first one, I have, and you don't have to do this, this is more for me, it's in the cognitive domain, we're going to look at this. It's in the cognitive domain, so the thinking domain. Have you heard of those before though, the cognitive and the affective and second motor? What, is it ed psych, or was that lesson?
We're starting to talk about it now.
Okay. So did you hear the other ones though, besides that, any other classes? So you don't, like your special ed hasn't really talked about that yet? Okay. So we'll look at that. So cognitive domain, but then like a medium level, because I'm asking you to use the GCF and the distributive part with factor polynomials, so you're doing something, so I feel like that's kind of medium level, not super high level. Solving problems is a higher level. So now here when I say solve problems, that usually is a higher level. Well, solving problems that are not, what's the word I'm looking for? Not typical. Like exercise, not something where it's just a memorized procedure where you actually have to pick something apart. Usually that's higher level because then you're getting into the analysis stage and synthesis stage. And just to explain what it means to factor polynomial, that's low because you can just memorize that. John just read it, right? You can explain it, you can memorize that, doesn't mean you really know, but it's memorizing is important. So that's low. And then when I say something like, I want you to appreciate the need for this, like I think hopefully through problem solving, you can look and say, hey, this skill is needed in order to solve some problems. Well, I just want to appreciate that. That's in the affective domain. That's your feelings and thinking kind of thing. And it's medium. And then work cooperatively is another affective domain as well. Well, I kind of do that for myself so I know that I'm trying to do things in different domains. So, yeah, maybe I should go over this a little bit slower than I originally thought. I guess I always think you can get over this and it's like a lot sooner. So on page 69 though, let's look at domains of learning. So that's what these are. These are domains of learning. And then taxonomies. You know, taxonomies are kind of like a hierarchy of learning there. So this first, it's on page 69, 70, 71, I guess. It's the cognitive domain. So, you know, if you had to, you're not sure what cognitive means, you know, you might put up there thinking. So this is like the thinking domain. So this obviously is where most of our objectives will fall. And then you have different levels in the cognitive domain. So the low levels are knowledge and comprehension. Middle level is application, so usually when you're applying, and a lot of times it's really, if you're trying to apply something to some new situation, it's your application. Unfortunately, I think, and I make the same mistake, is when I expect my students to just regurgitate like a procedure, use a formula multiple times, I think they're applying a formula, and they are applying a formula, but they're applying it to just an exercise, a common, that's what I'm looking for, not a common, traditional, but there's a word in there I'm looking for. I don't know if it's, but anyway, if it's just repetitious of using something, it's usually still in the low. I mean, it might be comprehension because they have to understand where to put the things in the formula, but it's not. They're not applying it to a new situation. So I might be able to get away with my problems up there, you know, applying a new situation. But once I do that 47 times, then it becomes a low level thing as well. And then your higher levels are your analysis and synthesis, which, you know, analyzing breaks things apart, synthesis puts them together, and evaluation kind of makes judgments about different things. So you know, look at the examples of the key words. In fact, you know, go ahead, John, read, and you'll see some overlap here. So it's really in how you use these words. It's not in the word itself. So the examples, read the examples there. Under knowledge, the low level there.
Recite a policy, quote prices from memory to the customer, that is the safety rules.
Right, so see those very basic, just memorization kinds of things. And some of the key words you'll use there. Brittany, what are the key words?
Arrange, define, describe, identify, label, list, match, memorize, name, outline, recall, recognize, relate, repeat, reproduce, select, state, and underline.
See, so when I have people just state something, that's a low level. You know, I just want you to memorize something, and there's nothing wrong with that. It's just realize that it's low level. You know, I want you to recite the quadratic formula. It's just low level. It's fine. Nothing wrong with that. You need to memorize the quadratic formula. And then, what does it mean to? So the definition there is recall data or information. As far as comprehension goes, understand the meaning, translation, interpolation, and interpretation of instructions and problems. State a problem in your own words. So some examples of that though. What does it mean to comprehend something? Gary, read those.
Rewrites the principles of test writing. Explain in one's own words the steps for performing a complex task. Translate an equation into a computer spreadsheet.
Okay, so you can see some of the things they have to do. It's not just a memorization, a reciting of thing, of something. They're actually trying to, you rewrite something in your own words, explain it. That's why there's a difference between, even on a test, you say explain your own words, but most people give it to you as defined in the notes. All they probably did was memorize it. And look at some of the key words there. What are some of the key words they're called?
Choose, classify, comprehend, convert, critique, defend, distinguish, estimate, express, explain, extend, generalize, give example, identify, infer, interpret, paraphrase, report, respond, rewrite, tell, and translate.
So if you go to, in here, if you go to page 85, and usually when we see cognitive domain, again, that's where most people focus because that's the thinking, the knowledge level. Here's what somebody's put together about how this really relates to math. So in level 1, now they're not calling it the same thing, but it is the same thing. It's still knowledge. It's just remembering. I have this knowledge. These are questions that we typically ask when we're asking to remember something, right? We define, duplicate, label, list, memorize, name, order, recognize, relate, recall, repeat, reproduce, state. Those are words that we typically see in a math or on a math test or in a math class. An example, student can recall a formula, name a shape, perform a calculation, repeat a process. See, when they're doing that, they're really just doing something very, very low. So I think you can probably see that most of our, lessons are probably at a very low level until we start asking them to solve a problem that you've never seen before. Think about something. Apply this in a new situation. We get them to repeat these procedures. And then a lot of times the argument is, well, you can't solve anything else until you can memorize these procedures. I don't necessarily know how true that is. And then we go to understanding level. Classify, describe, discuss, explain, identify, locate, recognize, report, select, translate, paraphrase. These again are words that we use that will or that we see oftentimes in math that are used to tell students to do something. So how about the student can describe what a formula does? So if I'm asking, I know you might be memorizing it, but if it's not exactly in the word, the definition there, what does it mean to factor something? Well, if you can explain it in your own words, then you're understanding it. You can classify shape from its properties. Express a final answer in the proper context. For instance, even that last problem, you might have done it correctly, but if you didn't put units squared on the end, I might say, well, you didn't really understand what you were doing. But it's hard to determine some of this stuff, right? Because classify shape from its properties. Well, what if I just memorize the fact that a trapezoid does not go into parallelogram family? Did I really understand that it doesn't? Well, no, until I can describe why it doesn't. Well, because the definition says this and it doesn't have this. Well, again, maybe I'm memorizing because the teacher told me, that too. So it's convoluted as far as which one is what level. When you get to application though, back on 69, it says use a concept in a new situation or unprompted use of an abstraction. Applies what was learned in the classroom in novel situations in the workplace. I mean, when you have a student that applies something from 3 weeks ago to this thing today, that's great. Then you can look and say, oh, you're applying something here that you learned before. Now I think you're moving up in the levels. Now you're at the middle level. So try to come up with problems that will teach or that will have them do that kind of thing. Give a problem, and when the students do struggle with it, you ask them, well, think about how you can use what we learned before to maybe apply here. Example, they can use a manual to calculate an employee's vacation time. So they've never done this before, but they can apply their knowledge to doing this. Apply some laws of statistics to evaluate the reliability of a written test. So they've never done it before on this test, but now they're applying what they've already done. There are some math words in there. Look, apply, change, compute, construct, demonstrate, discover, dramatize, employ, execute, illustrate, implement, initiate, manage, modify, operate. And then, you get down to the bottom there and it says what? Show and solve. Again, you gotta be careful with the solve part. Just because you tell them to solve a problem doesn't necessarily mean that they're applying their knowledge. You see what I mean? It doesn't mean they're applying it. They might just be memorizing, something. Giving them a new novel situation and having them apply it, that's what it's really meant. And maybe on the application on the page 85 there, again, same kind of words: choose, demonstrate, dramatize, illustrate, interpret, operate, solve, use, right? Student can select the proper formula for a task, solve an equation, complete a proof, translate a complex real-world situation into symbols. Usually when you're saying solve, you're usually talking about taking a word problem, not an exercise. Again, it might be just repeating a process, but. And the other ones are tougher. Analyzing. If you're asking them to compare and contrast and differentiate between two things, distinguish, what if this would happen? I mean, these are in my class, at least I know that in class, I probably present more kind of what if situations, like let's analyze things, but that's because I'm there as the guide. But then when it comes to homework that they're gonna do outside of class, then you end up giving them low-level things, and same thing with tests. You end up giving them low-level things because they're easy to assess. You're not really creating anything at the top level until you're asking them to derive a formula or something like that. So, and we'll work on these as we go. We'll say, okay, is this a high level or is this a low level? And actually, these kind of all go together here. So go to 77. All this stuff is kind of for you to peruse as you. So these are some examples, and these are examples from all different subject areas. So if we just look at the cognitive ones, so here are some low-level cognitive. So the first example is low-level, but it's in all three domains. The first couple here are cognitive. Identify, locate 7 continents from 4 oceans. Okay, well, it's not for us really, but you see the gist of it, right? The student will describe the method for making a color wheel. Well, maybe number 4 is math, right? If you're just identifying independent and dependent variables within a given situation. Now, I don't know if I would consider that low if they had to read a problem and determine which is the independent or dependent variable. If they were to just look at an equation and say the x is the independent and the y is the dependent, then I could see that being low. But if you are saying, if you have a word problem and you're talking about time versus profit or something like that, for them to be able to say the time is the independent and the profit is the dependent. Well, I'll tell you what, in the interest of time, we'll just divide you a break before the next class. We'll kind of stop there, and you've got things to work through. Work on, or read through some of these objectives, and kind of get a feel for that. It'll probably help you in your insight class as well. And start working now that you've seen an example of a lesson plan written, and even taught from the perspective of like how we want to kind of model lessons. Consider a lesson you taught in the field, get working on your lesson plan. And then next week in the middle of, while we're thinking about our lessons, then we'll start talking about, well, what do we know about research on learning theories and how we ought to teach our students based on how they learn. So hopefully I'll be feeling better.
What day do you want our paper?
Okay. Well, it's next week. I know that means most of you will turn it in on Friday.
Okay, that's what I'm saying.
And that's fine. It's just, but any time during the week, that's fine.
Okay.
here's your, she didn't write anything on the back, but she emailed me and said you guys did a really good job
She loves
doing
us.
everything, so. She wrote some things on the back, I didn't get your guys yet.
Oh, gee. She's right, good lord. I don't know how that.
Well, sometimes they don't,
We got-
always submit them either, and I don't hound them too much because it's not like they got paid for.
Well, she said that she was gonna pull one out.
Oh, did she? Okay.
She like brought it up.